welcome back to another celebration of mine. And without further ado, I will introduce our presenter today. Philipp Legner is the founder of Mathigon, which is an award-winning platform for math education. He studied at Cambridge University and math education at UCL, and worked with companies like Google, Bloomberg, and Wolfram Research. So it's a great pleasure to have Philipp here to talk about fantastic folds, and I will pass over to you, Philipp.
Thanks for this introduction. Thanks to everyone who came for this presentation. And yeah, it's a real pleasure to be here and talk to you today. Like Thiago said, I've studied mathematics, but then worked as a software engineer for many years. But during that time, always on different educational projects, some of which I will talk more about towards the end of the presentation. And that means that over the last 10 years, I've spent a lot of time thinking about how to teach mathematics. How can we make it more fun and engaging and accessible for kids as well as adults, and both in classrooms as well as on online digital tech platforms, during outreach projects, and in many other settings. And there's one topic that kind of popped up all the time and that seemed to tick all of the boxes for what I was looking for, and that is origami. Origami is colorful and visually beautiful, which you don't actually find that often in mathematics, and especially in the school curriculum, which can be very abstract, equation-based, and black and white. Like, we don't have a James Webb telescope that takes amazing pictures, or explosions in chemistry, or cute animals in biology. So we have to work a little bit harder to make mathematics visually fun for students. Origami can also be practical and hands-on, folding and experimenting with physical paper. And that's especially important for younger students, rather than just seeing things written down on paper or on a screen. Origami has some really important applications in real life, and again, we'll see many of them later. And it also showcases how creativity and art plays into mathematics. And all of these things can help us reach students who might not otherwise be interested in mathematics or enjoy learning about maths. And maybe most importantly, origami has a very low entry bar and is accessible to everyone, but then has a high ceiling with very advanced and surprising mathematical topics. And we'll try to get a bit closer to that very high ceiling during this presentation. Euclid's axioms. So lots of things going on, but basically we can construct two different things. We can draw lines and we can draw circles. And similarly to this, there are some origami axioms that define everything that's possible when we fold paper. And there are 7 of these. I'll have some animations that show what they are. So you can fold a line that goes through any 2 points. If you have 2 points, you can fold a line that places 1 point onto the other one. You can fold a line that places any line onto another line. You can make a fold that is perpendicular to one line and goes through another point. You can fold a line that goes through a point and places another point onto any existing line. You can simultaneously fold 2 points onto 2 lines. And the last one, you can fold a point onto a line by making a fold that is perpendicular to another existing line. So to say it out in words sounds a little bit complicated, but hopefully these images make it quite clear what's going on. Of course, all of these axioms assume that paper and folds are infinitely thin and infinitely accurate. The first 6 of these axioms were first published in 1992 by the Italian-Japanese mathematician Humiaki Hosita, and the last one, the 7th axiom, was discovered in 2001 by Koshiro Hattori. And what's really fascinating is that this set of axioms is not equivalent to Euclidean geometry. In fact, it is more powerful, and that's mostly because of the 6th axiom. Placing 2 points onto 2 lines is not possible just using straight edge and compass in Euclidean geometry. And yeah, during this presentation, we will see what that actually means and what that allows you to do by folding paper that you can't just do with a straight edge and compass. Let's start very simple by seeing which numbers we can fold. So we assume you've got a piece of paper that has a side length of 1, and we can fold it in half to construct the number 1/2. In fact, we can fold any rational number, and we can show that quite easily using induction. So let's assume that we can fold a ratio 1/n like this. And then let's make 2 diagonal folds across the paper and 1 more vertical fold like this. And if we look at the similar triangles that we have created, looking at the ratios and simplifying things a little bit, it's quite easy to show that the distance x in this case is 1/n+1. So by induction, we can construct any ratio that is of the form 1/x. And because we can easily combine multiple of these ratios and line them up, we can, in fact, construct any rational number like this. And when working with children, I might stop at this stage and spend a lot more time talking about what induction actually is and what's going on here. But let's go beyond that, because we should already know that we can construct some numbers that are not rational, like the diagonal of the square, for example, is square root of 2, which is an irrational number. And in fact, we can solve any quadratic equation using origami. Let's consider we have an equation of the form x squared plus px plus q equals 0, where p and q are any rational numbers. And we already know how to construct p and q by the previous slide. On our piece of paper, let's fold a coordinate system with 2 perpendicular folds like this, and then mark a couple of additional points. We'll mark the point -pq, the point 0, 1, and fold the line y equals -1. And again, if we assume that we can construct p and q and 0 and 1 as well, we should be able to find all of these points and lines on our piece of paper. And now what we'll do is we'll make a fold that goes through the point -pq and places the point 0, 1 onto the green line y equals -1. So here you can see the fold happening. The purple and the pink lines should be perpendicular like this. And it turns out that the x-coordinate of this intersection with the x-axis, the purple point that just appears, the x-coordinate of that point is a solution to the quadratic equation we have. In this case, it would be a small negative number. If you try this using paper, you can see that in some cases, it's impossible to make a fold like this. In some cases, there are 2 different possible folds you could make like this, showing that the quadratic equation could have no 1 or 2 solutions. And the proof why this works is pretty simple and just involves some coordinate geometry, but I'll leave that as an exercise for today. Quadratic equations can also be solved using straight edge and compass geometry, but with origami, we can go one step further and even solve cubic equations. And that is something that's impossible in Euclidean geometry. Let's assume in this case that we have an equation x cubed plus ax squared plus bx plus c equals 0. And again, we start with a coordinate system on our piece of paper and a couple of lines and points like this. So we've got an orange and a green line and a blue point and a pink point. And you can see for the pink point and the green line, the y coordinates are the same, and for the orange line and the blue point, the x coordinates, in this case -c and c, are the same or reflected across the y axis. And using the 6th axiom that we defined before, we can now fold simultaneously the blue point onto the orange line and the pink point onto the green line like this. We get a new purple fold that you can see here. And it turns out that the slope of this purple line is a solution of the cubic equation. Again, I will leave the proof as an exercise, but the way one way how you can derive this is to look at 2 different parabolas. The parabola that has the pink point as a focus and the green line as a directrix, which is sort of a normal upright parabola, and then a tilted parabola that has the blue point as a focus and the orange line as its directrix. Here are these 2 parabolas. The purple fold that we've made is tangent to both of them, and you can use that property to find the slope of the purple line and then verify that it does indeed satisfy the cubic equation at the bottom. Like I said before, cubic equations cannot be solved in normal Euclidean geometry, but we don't even have to stop here. We can also solve quartic equations using origami. And the way to do that is use some Galois theory and resolvents and just convert the quartic equation into a series of quadratic or cubic equations that we can then solve using the methods we've already seen. I'll skip over those details, but as you might suspect, quintic equations or higher order polynomials unfortunately cannot be solved even using origami. Otherwise, we could then derive some kind of general solution for the quintic equation using coordinate geometry. And one thing that you might have also noticed is a pattern in those two examples I've just shown you. In the quadratic equation, we placed 1 point onto one line. Here we placed 2 points onto two lines. And in fact, solving a general nth order polynomial can be shown to be equivalent to placing n-1 points onto n-1 lines simultaneously. And yeah, there are some really fascinating geometric reasons why that works. But let's take a step back and think about all of the numbers that we can now construct using origami. And again, this is not a fully formal proof. There are lots of things to verify still, but this should give you a general idea. So let's call O the set of origami numbers. And we already know that all rational numbers are in the set of origami numbers. And we also can write a cubed of x as the solutions of all cubic polynomials in x, where x is some kind of field. And then we also have all of the cubic polynomials that have rational coefficients. But once we've constructed a new irrational number, we can again use that as a coefficient for a new cubic polynomial. So we kind of get this this infinite recursion of nested polynomials that we can construct. The set O turns out to be a field because we can add and subtract and also multiply and divide these origami numbers by folding paper. And it is a superset of all of the numbers that you can construct using Euclidean geometry and ruler and compass. But it is the same set of numbers that you can construct if you instead have a marked ruler. So a straight edge where you can place your own marks and points along the line. Then you sort of get the same set of numbers that can be constructed. And a small aside here, you can work out which regular polygons can be constructed using origami and folding by looking at complex roots of unity. Those form a regular polygon, and if the real and imaginary parts of all of the vertices of these complex roots are in the field O, then the polygon can be folded, otherwise it can't. For example, you can check this that regular heptagons can be folded using paper, even though they can't be constructed using straight edge and compass. In fact, talking about things that can't be done in Euclidean geometry, I'm sure you're all familiar with these impossible problems from ancient Greek, in fact, that aren't possible in Euclidean geometry, trisecting angles, doubling cubes, and squaring the circle. Doubling the cube essentially means constructing the third root of 2. And I mentioned before that you can't solve cubic equations using Euclidean geometry. Squaring a circle essentially means constructing the square root of pi. And trisecting the angle is a little bit more complicated to think about, but you might know that the triple angle formula is sine of 3 theta equals 3 sine theta minus 4 sine cubed of theta. So this also is a cubic equation. And trisecting the angle is basically equivalent to finding a solution to this cubic equation, which we know we can do using origami. We can also construct cubic roots. Unfortunately, the square root of pi is transcendental. And so yeah, that problem can't be solved even using paper folding. Trisecting the angle, thinking about it like this sounds very complicated, but in fact, there's a really clean and beautiful construction method, which I just wanted to show you very briefly. So let's again assume we've got a piece of paper like this. We've got an arbitrary angle alpha given by a line like this. Let's quarter the paper into 4 strips like this, and let's add a couple of labels. So we label the lines L and K and the points P and Q. Since trisecting the angle isn't possible in Euclidean geometry, we know that we probably have to use this special 6 axiom with placing 2 points simultaneously onto 2 lines. And exactly that's what we're going to do now. We'll place Q onto line L and P onto line K, like this. And the labels have disappeared, but there they are. So we make a new fold like this, placing Q on L, P on K. And you can see that the line K kind of wraps around the corner, around this fold that we've just made. And we'll extend the line K to go through the entire sheet of paper like this as a diagonal. And that's basically it. We've trisected the angle. We can bisect very easily the bottom half of the angle again to get our 3 different segments. But yeah, it's that easy to trisect angles just using origami. And as it turns out, there's very little that you can't do using paper and folding. The fold and cut theorem, which was proven in 1999 by Eric and Martin Demain and Anna Lubev, says that any shape made up of straight lines on a piece of paper like this, and the lines don't have to be connected, you can have multiple different polygons or holes or disconnected lines. Any shape like this can be created using a series of flat folds and then a single straight cut. And so here you can see the folding pattern for this one in particular. And I hope you can still see my face as well, small at least, because I wanted to show you what this actually looks like in practice. So I've got a square piece of paper like this. I've pre-folded it a little bit to speed up the process. So we'll fold it in half. We'll make some half and quarter marks along the side. We'll keep folding it up like this. And now I'm going to make a single straight cut along this pre-marked line, like this. Ooh, and I shouldn't have used cardboard for this demonstration because the cutting is kind of difficult. Let's hope this still works. So I've made a single straight cut. I'm going to unfold the paper and we've created a star like this. And yeah, like Eric, Martin, and Anna proved in the fold and cut theorem, this doesn't just work for a simple star like this. This works for any shape consisting of straight lines. There's some interesting computational geometry that goes into finding a fold pattern that produces a cut like this. And in fact, they also created a font that has the folding pattern for every letter in the alphabet. So here you can see a few more examples of different shapes that can be created by following these folds and then making a single cut. And yeah, like Colin said, in this case, you might have to use a ruler to work out exactly where the folds are. It's not just about folding without scissors or other tools anymore. But yeah, a really fascinating result. Here's a different problem related to folding that I've been working on. So one of the projects that my company built, one of the tools is called Polypad. And this allows students, it has hundreds of different tools and features, but one of the things we allow students to do is to create arbitrary nets of polyhedra like this, and then just select all of the polygons and press a button that folds it into a 3-dimensional object like this. And while this is conceptually very easy to think about and very intuitive, even for primary school kids to play around with, there were some very big technical challenges in building this. So we've got our set of polygons on the canvas. We can work out which ones share an edge and kind of create a spanning tree of the net. But then we have to work out how much to fold all of these hinges, all of these edges along which the polyhedron folds. This is a really simple example because you only have 3 polygons meeting at every vertex. And if you only have 3 polygons, that means the vertex by itself is kind of rigid. There's no movement possible. And you can use some very complicated trigonometry to work out the dihedral angles along these hinges by which we have to fold. But as soon as you get more than 4 polygons meeting at a vertex, the vertex by itself is no longer rigid. So rather than looking at every vertex individually and working out how much we have to fold, it's sort of a very complex computational geometry problem where we have to use collision detection and some numerical methods to work out how far to fold the polygon. And even after a lot of work, there are still lots of edge cases where we just have to show an error message and say this isn't possible, or where we have to default to some fallback values, like just folding every edge by 90 degrees or something like that. And one of the reasons why this is such a complicated problem is that there isn't always a unique solution. Here's a tweet from 2007 by Mathigon that shows the same net folding into two completely different polyhedra like this. In fact, I will play that animation one more time. So you can see we start with the same net and we fold it into two different cuboids like this. And this is just using squares. You get much more complicated problems if you allow arbitrary polygons. If you are interested in learning more about this specific problem, there's a really great Matt Parker video on YouTube that shows many more different examples and practical examples of folding these equal nets of made up of squares into different polyhedra. We can also try to invert this entire process and think about unfoldings. So rather than starting with a flat piece of paper or with a net, we start with a polyhedron and we think about which polyhedra can be cut and unfolded into a plain non-overlapping net. So the net that you want to end up with has to make physical sense. You can't have multiple bits of paper overlapping. And there are two different types of unfoldings we can think about. We can have edge unfoldings where we just cut the polyhedron along its edges and then unfold it. This is, I guess, what we normally think about as nets and foldings. But we can also have more general unfoldings like this one, where we can cut anywhere along the faces of the polyhedron, try to unfold it and see what we end up with. Edge unfoldings aren't always possible. Here you can see one special type of polyhedron. It's non-convex, which makes it a little bit harder. We basically have two boxes stacked on top of each other. And if we were thinking about unfolding this just along the edges, you can kind of see quite easily that the hole in the face that forms the top surface of the bottom cuboid, the hole in here is not big enough to fit the entire net of the smaller cube on top. But there's no way for the paper that is needed for the smaller cube to come from outside the hole. So this polyhedron doesn't have any edge unfolding that is possible. And let's think about all the different combinations. So we can think about convex polygons and non-convex polygons, edge unfoldings and general unfoldings. And we've just shown that not every non-convex polygon has an edge unfolding. It is also possible to prove that every convex polygon has a general unfolding. So maybe not just cutting along the edges, but if we can cut anywhere along the faces, the surface of the polyhedron. Sorry, those should say convex polyhedron, not polygon, if anyone spotted that. Every convex polyhedron has a general unfolding. But it turns out that the other two cells are still unsolved problems. No one knows whether every convex polygon has an edge unfolding. More importantly, no one has found a counterexample. No one has been able to prove that a specific convex polyhedron doesn't have an edge unfolding. And similarly, no one knows whether every non-convex polygon does have a general unfolding. If you want to learn more about foldings and origami and a lot of what I've talked about, I would really recommend this book by Eric Demain and Joseph O'Rourke, which goes into a lot more detail and is incredibly fascinating. And many of you will know that Eric Demain has given lots of talks at G4G before and maybe even know him. But this sort of ends the technical part of what I wanted to talk about. Let's think a bit more about the history and the applications of origami. So the word origami comes from the Japanese oru, which means to fold, and kami, which means paper. And Japanese monks were among the first to practice origami in history. Japanese weddings used two paper butterflies to represent the bride and groom, possibly as early as the year 800, just after paper was introduced to Japan from China. The fact that paper is not very durable means that there isn't much material evidence, but over time, origami became much more about recreational use rather than ceremonial use in weddings, and many new folding techniques were developed. So modular origami, for example, is a technique where the final shape is assembled using multiple different pieces of paper that are all folded individually. Up here on my bookshelf, you can see lots of polyhedra built using modular origami. Wet origami is another folding technique where you start with slightly damp pieces of paper that allows for smoother folds and a more organic look. And kirigami, I think this was mentioned in the chat before, also allows you to cut paper while folding. So there are lots of different variations of origami. Here you can see the famous crane, and here are lots of different cranes stacked on top of each other to purchase. But origami, like I said, is not all about mathematics or about art and recreation. There are some very real and important applications in everyday life. One of these applications is airbags. So the origami artist Robert Lang worked with car companies to develop computational models of unfolding airbags to ensure that they inflate quickly and uniformly and are safer for passengers. Origami can be used to design efficient packaging that can be produced quickly, has a large volume to surface ratio, and very few overlapping seams. The British and US military used ideas from origami to develop foldable bridges that can be deployed quickly during military operations, or to give access to emergency vehicles after earthquakes and tsunamis. So if bridges were destroyed during an earthquake, it's important to replace them quickly to give access to aid. And this image here is a prototype developed at Hiroshima University for that. Other scientists use origami to develop houses that fold and compress rather than crumble during earthquakes to better absorb the energy. And other engineers are working on origami houses that can be mass-produced, then transported and unfolded when they reach their destination. One of the most exciting applications might be in satellites. So satellites need large solar panels to generate power, but rockets, as you know, have very limited space. So we can use origami techniques to unfold solar panels once they reach space, so that they take up very little space during launch. And the goals here are very, very efficient folding, very few motors, very few mechanical components. And one famous example of this is the Miura map fold. This was invented by the astrophysicist Koichiro Miura in the 1990s and used by the Japanese Space Agency in 1996 and after that. So you can see the folding pattern here. It's not all straight lines. You have lots of parallelograms, and I actually have a practical example. And what's so cool about this fold is that I only have to pull on these two opposite edges to unfold the solar panel like this, and I can push on those two edges to fold it up again. So very satisfying fold to make yourself and to look at, and that reduces the number of moving parts and motors required to unfold these solar panels in space. You might have seen similar things like this also in nature. So the fold animation I've just shown you physically looks very similar to the wings of earwigs. Here you can see a zoomed in example of those insects. And when opened, the area of these wings actually expands by a factor of 10, which is the highest folding ratio ever found in nature, both in animals and plants. And when expanded, these wings snap into rigid position so that the insects can fly, but it only takes a very light touch for them to retract again into the body. And here's an animation. I hope this you can see this through Zoom of how these wings expand and contract. Scientists can study these folding patterns and these plants and animals and try to mimic their abilities in technology. And potential applications could include foldable electronics in smartphones, or even self-folding camping tents that can be deployed very quickly. At an even smaller scale, origami is also used for medical stents. These are inserted into patients' blood vessels in order to enlarge clogged areas. They were first developed in 2003 at Oxford University. And here on the right, you can see what they look like initially folded up so that they can be quickly and easily transported to where they need to go. Then they can expand and sort of expand the arteries and veins. And they are both cheap and versatile to produce, but the orthogonal and vertical and diagonal folds also make them very strong and flexible inside patients' bodies. There are places in nature where we use folding, so not just earwigs, but rocks fold like this. Some images of rock formations that developed over hundreds of thousands of years by tectonic plates pressing together. Here's another example in Ireland of chevron folds. And again, you can use mathematical techniques to study how these folds form based on different forces. And other places in nature where we see foldings are proteins in our own body, or at a, again, much smaller scale. I don't really want to go into too much detail here. You could probably do entire presentations just about these topics, but I thought it would at least be important to mention proteins are very long strings of molecules that can be several meters long, and they use electromagnetic attractions between consecutive molecules and atoms to fold into these three-dimensional rigid structures. And once they're folded up, they can perform different actions, but they also don't get tangled in your body, which is very important. I think if you put together all of the DNA strands in your body, it would reach to the sun and back in terms of distance. And the process here, of course, is very different compared to folding paper, but there's some similar mathematics using linkages and dihedral angles that you can use to look at how these proteins fold. Now, at the very beginning of my presentation, I said that I really liked origami in education. And one question, I know that this is a somewhat selected audience, but one question you might ask is, how is origami useful for passing exams? How can that help students? In fact, I found this little video clip from a movie that you might recognize, and I hope you can see and hear this correctly now with Zoom sharing.
It is the view of the ministry that a theoretical knowledge will be sufficient to get you through your examinations, which after all is what school is all about.
So yeah, I hope you saw that. School being all about passing examinations, of course, we know isn't true. I feel like exams are sort of a necessary evil that we need to have to evaluate how students are doing. But of course, school should be about learning skills that you need in life. And in fact, the skills in exams can be very different from the skills you need in life. You can probably pass many exams without really understanding the underlying mathematics, just by memorizing how to solve lots of standardized questions. But that does bring us to the next question. How is origami useful in everyday life? We did see lots of real-life applications before how origami is used in science and technology and nature, but only a tiny proportion of math students will actually work in fields where they use these. Maybe a few hundreds or thousands compared to the millions of students that we make study maths every day. But the same can actually be said for many other topics in the math curriculum. And I'm not sure, but what's the last time any of you used quadratic equations or trigonometry or calculus in everyday life? Of course, these all have important applications, and we want as many students as possible to be interested and then study STEM subjects to research, to become researchers or engineers and develop new applications. But the vast majority of students are not actually going to use these specific topics. So that, I guess, brings up a much more philosophical question. Why do we even teach mathematics? And there are some topics in the math curriculum that do have an important application for many different students, like simple arithmetic or data science. You want to understand what charts in newspapers mean and learn about climate change and elections and so on. There are some other areas of mathematics that are also really important in everyday life that are not taught in school, like cryptography, for example, and we should probably change that. But this is sort of a small part of the mathematics curriculum overall. But just because a certain topic in the math curriculum isn't useful for in everyday life for a large number of students, doesn't really mean that mathematics doesn't have applications. Many puzzles and problems in mathematics teach important skills like problem solving or critical thinking or creativity. And these skills you learn while studying mathematics are incredibly useful and versatile for a vast range of topics, even if the specific problems you study are not that useful. And finally, I just want to say that not everything we teach in mathematics has to be useful. Just like learning about Shakespeare or Mozart is not useful in a sense in everyday life. Instead, I think the criteria for picking what we teach should be more that it's meaningful, that it gives us some new insight in how our universe works, or interesting history, or just because it's really beautiful. So there are these different levels of mathematics that we teach in schools, some that are more application-based and useful, some that are more about learning skills like problem solving and abstraction and critical thinking, and some that just help us understand who we are and how our universe works. Unfortunately, a lot of our existing curriculum doesn't fall into any of these categories. And this is one of the reasons why so many students dislike mathematics. And this is really what I try to solve with the project I've been working on for many years now, called Mathigon. It started out just as a spare time side project I started after university, almost like a personal blog where I shared interesting problems and lesson plans and ideas, trying to make mathematics more engaging for students and more interactive. And I've got a little video here that just shows some of the types of content that is available on the Mathigon website. All of this is completely free to use for students and teachers, and you don't even need to create an account to access it. My goal with Mathigon, well, I had two goals with Mathigon. One was to make the curriculum a lot more engaging for students. So rather than teaching about abstract equations and procedures and algorithms, every course has an interesting storyline that shows why learning this specific topic is useful or interesting or important for students. Those stories can be about history, about real-life applications, completely fictional stories about where mathematics appears in nature, and many different types of stories. The second goal was to try to make online learning a lot more interactive, so that students don't just watch a video or listen to a lecture or do what the teacher tells them, but students can actively explore and participate, make their own discoveries, be creative, and yeah, learn in a much more interactive and active way. Topics cover both parts of the standard curriculum that you have in schools, like Pythagoras, for example, or trigonometry here, but we also have courses about graph theory or non-Euclidean geometry or cryptography and many other topics that are incredibly fascinating and somewhat new in the history of mathematics maybe, and therefore don't appear in our curriculum. There's one project that I wanted to show you in particular that we've been working on very recently, and that isn't related to origami, but has, I feel like, has very similar goals of connecting mathematics with a completely different area of study, in this case, music. So you've seen Polypad before for some of the folding nets we've built. Polypad is just an empty canvas. You have lots of different tools you can drag onto the canvas. We can create nets. We can create our own custom polygons and move them around. There are lots of other tools not related to geometry, like number bars or number cubes like this. We can split these number cubes to think about decimal representations. We've got fraction bars. We've got dice you can roll to generate random data. You can then tabulate that data and run simulations. But one thing we've added just in the last few months is music and audio. So if I select a shape like this, there's now a play button at the bottom. And if I press play, you should be able to hear one way of what this polygon sounds like. If we look at this custom polygon that is not regular, you can see that it sounds differently. It has a different number of vertices and different length of edges. And you can listen to just the edges, but there are lots of different types of animations. So I can select the area, for example, as an animation. And now if I press play, the polygon will fill from the bottom, almost like a water bottle, and the pitch will change as the water level height changes. Or we can listen to the angles inside a polygon and see what these sound like. Our goal with these tools is both to get students who love music excited about mathematics, but also get students who like mathematics excited about music and what they can do with mathematics. And one really important other side effect almost of this is that Polypad has just become a lot more accessible to students with certain accessibility issues. So we spent a lot of time over the last 2 years designing these beautiful visualizations and graphics for the website. And now students who can't see can actually hear these shapes and hear what they sound like. One activity that lots of teachers have started doing is they create a specific shape, they cover it up, and then play what the perimeter sounds like or what the angles and the area sounds like. And just by listening to the sound, try to have students guess what shape they had made. And maybe the perimeter on its own isn't enough, but if you have both the perimeter and the angles, you can kind of estimate what the shape might look like. This works not just for all of the different types of polygons, but also for many of the other types of manipulatives we have in here. So if we have some fraction bars, we can even pick different types of instruments and then play them together. And create different types of rhythms. And there are other tools down here to put all of this into context. So I can create a song maybe like this that uses a few different types of polygons in sequence, like this. And you can create these songs like this and then export the MP3 files. And what we've had people start doing is create little TikTok videos of music and sound and rhythms generated using these mathematical shapes, which is really fun to see. That's the end of my presentation, I think. Thank you so much for joining. I hope this was fun and interesting. I know it went into a few different topics towards the end, but yeah, let me know if you have any questions, or we can go straight into Gathertown and talk more there.
So thank you so much, Philipp, for the very broad talk and very, well, colorful and soundful one too. So I've been monitoring the chat. So people are praising Polypad, multiple people saying how nice it is designed and how much they use it. So Paul, who has written a lot of questions in the Q&A, I will give the rights to talk, and go ahead.
Hi, I put some questions in. I'm actually shopping right now, so you can meet me again. But any of those questions, I guess you inspired me.
Thanks so much for these questions, Paul. Really cool ideas. And I don't know all of the answers, but we can go through some of them. So the first question is, you can use folding to perform computations, like to find factors of certain numbers. What would be the computational power of a folding computer? Could it find primes? And To be honest, I've never thought about that. I don't think I can give a reasonable answer on the spot now, but I will definitely look into that some more and maybe yeah, let you know if I find any research or have any good ideas later. You can divide numbers using paper folding. If you have sort of two different lengths as distances on a piece of paper, you can divide them and find the ratio. I'm not sure if there's a way to work out whether numbers are integers or not, or rational or not, just using paper folding, which I guess you might need to determine which numbers are prime. Applications in robotics, absolutely, lots of different applications in robotics with kind of folding arms. And again, for example, if you have an arm consisting of two elements, finding the most efficient way to move the hand to a certain destination, how do I fold, what angles do I use? Maybe not origami, but definitely related to folding. Is it meaningful to consider fractal folding? I've not really thought about fractal folding, but I hope that my talk kind of mentioned to an extent how much open research there still is to do in this whole area of mathematics around folding. So yeah, I will keep thinking about that. And last question, I find it useful to fold US paper into a ruler when I need one. International paper uses the golden ratio. Can you derive whole numbers from the golden ratio? Let me think about that. I feel like if you don't have anything else, you always have to assign a certain number or distance or unit to one length that you have. So that could be the length of the edge of a piece of paper. And what we did at the beginning was say that the paper has dimension 1, or it is 1 unit long, and then from that as a starting point, we can fold other numbers. The golden, if you just have that one distance, the golden ratio itself cannot be folded because no, it can be folded because it is a solution of quadratic or cubic equations. So yeah, you should be able to fold the golden ratio just starting from a piece of paper with side length 1. And that, I think, means that if you start with a paper that is in the golden ratio, having that second distance doesn't really give you any new information, because you could have found that distance just starting with the original edge of the piece of paper that you already have.
So we have another question from the attendees. You should be able to unmute yourself.
Hey, Philip, this is Suyash. I really liked your presentation and the tool. And I was wondering, so I've seen tools like this and another company, Brilliant, and a few other tools that present these things in a very nice way. And I'm wondering, like, have you done from your own research, or what are your thoughts around getting these to get kids interested in STEM, like, you know, like seeing music through the shapes? Does it also really teach them something, or does it just kind of makes it more fun to, you know, like maths in a fun way?
I think it does a bit of both. It definitely makes it more fun. And we've seen so many, or we've received so many emails or tweets from teachers using some of these music tools in the classroom and getting students really excited about composing. But it definitely also helps with the understanding, and just for especially very young students, having a nice animation and visual together with some audio that shows the difference between the perimeter and the area and the angles of a shape and what these actually mean. I love Brilliant. There are lots of other interactive tools, whether it's Desmos or GeoGebra. One thing that we focus on a lot is that we want students to be as much of a creator as they are the consumer of this content. So we don't just want some activity author to build a really engaging, fun activity and then students have a slider underneath, they can move and see what happens. We want students to be able to author these activities and songs in this case, or simulations on their own. So we try to create lots of different types of tools and this very open world canvas for students to be creative and explore and come up with new ideas for how to visualize things rather than just seeing things that other people created.